Hey all, today we're going to resume uh, our new learning. We got to talk about probability here before the AP exam. I'm going to try and do my best to keep it short like I normally do. Going to try to keep it like we normally do. I am missing a smartboard to write on, but we're going to do our best here. Make sure that you email me or send me a message on Teams with any questions you might have since we can't meet face to face. I'll be available during office hours and also during the instructional time. So basically 4 hours, 3 days a week. And you can always email me anytime you need to, and I'll try to get back to you as soon as I can, of course. So we're going to start today talking about sort of the basics of probability, and then over the next few weeks we will work through the next few chapters of probability. And I'll also be asking you to do some review through the AP website, and you could take advantage of the other reviews, some YouTube videos, some really great teachers out there doing things to help kids prepare for the AP exam. So we're going to start with a little bit of definitions. I think I tell you in the directions for this week. Write things down if they will help you. If not, then it's good to listen, experience this stuff, and you can always take screenshots or something to look at later for practice or studying. So we've talked about randomness a lot this year, and sort of to define it, a random thing that happens is something when we know the possibilities of what could happen. The thing that we don't know is what possibility is going to present itself. So flipping a coin, we know that there's two possibilities. What we don't know when we flip that coin is which thing happens, the head or the tails. Sometimes we like to say, hey, pick a random sports team, or we'll tell somebody to say, hey, give me a random name of something, and that's not necessarily random uh, because it's affected. If you ask me to shout out a sports team at random, I'm probably going to say one of the teams that I'm most interested in, and so therefore, it's not a random phenomenon. A trial is one attempt of a phenomenon, so I'm going to stick with the basic coin flip. One trial would be one flip of a coin, and that should say one, not on. I'm sure I'll get an email from somebody. An outcome is what happens, so we're flipping a coin. Flipping a coin is the random phenomenon. One coin flip is a trial, and the outcome is what we see, a head or a tails. And then we have things called events. So it's a collection of outcomes. We usually name these events with capital letters like event A, event B, so on and so forth. And so, for instance, maybe I'll flip two coins and then I'll see what I get for each coin. And maybe I get a heads and a tails. That is an event. The sample space is all possible outcomes that you can get. So if I flip two coins, what are all the possible combinations I could get when flipping those two coins? So I can get a heads and a heads, a heads and a tails and a heads, and then a tails and a tails. So maybe I flip the same coin twice. And notice we usually write them in set notation with these curly braces. We call this event, this sample space, capital S. So I'm probably going to be talking about probabilities today, some things that you already maybe have some mastery with. So don't think that I'm talking to you like you're ignorant, but it's good to go over this stuff together. So again, we're calling events by capital letters, so we're just going to call this event at A. And so the probability of any event A happening is the number of time that thing actually happens divided by the number of trials. So this is an observed probability. We've used this type of notation before, this P with P of A. This is the probability of A. We've done that a lot. Like we've been trying to find the probability of a mean being greater some value, or the probability of a sample proportion being greater than some value. When we were talking about hypothesis tests, we're going to write our probability statements the same way in this type of probability. So this is something I'm sure you are comfortable with. And so when we're not actually running some sort of experiment or simulation and we know this theoretical probability, that's called, well, it's called theoretical probability. So we know theoretically that there's a 50% chance or a 0.5 probability when I flip a coin of getting a heads and a 0.5 probability when I flip a coin of getting a tails. 1 in 6 probability of rolling any number on a 6-sided die. Those are theoretical probabilities. We can get observed probabilities or experimental probabilities by actually doing those things, flipping coins, rolling dice. And in your experiment or your collection of trials, you might not get the exact probability you would expect, and that's okay. So here we go. There's my example of the probability of getting a heads. I'm going to talk a little bit more about that observed probability versus theoretical probability on the next slide. And then we have this thing, this like personal probability. You know, people like to quote statistics that don't really have any empirical evidence. Like, I think my example in here is about your chances of passing an AP exam or getting a 3. I have about a 20% chance of getting a 3 on the AP exam. You don't have any foundation for that type of probability. So we call that a personal probability. It's what you believe, because you don't have any empirical evidence to show that you have a 20% chance of getting a 3. You might just maybe not be as confident as you should be, and everybody here should be confident because you've been working all year. So let me take it back to that last slide. Like I said, I was going to compare the experimental to the theoretical probability, and that's where the law of large numbers comes in. And so we know that the more you sample, the better off your information is from doing hypothesis tests and confidence intervals and sampling distributions. And so if we were to repeat that random process, flipping a coin over and over and over, and instead of maybe flipping it 25 times, I flipped it 1,000 times, I would get a ratio of heads that show up to number of coin flips that gets closer and closer and closer to 0.5. And that's what we call the probability of an event. And so the more we repeat the random process, the closer our experimental probability gets to matching our theoretical, or what we believe is the actual probability. So if we did flip a coin 25 times and get 9 heads, does that really mean that the probability of flipping a coin and getting a heads is 9 out of 25? Well, the answer is an emphatic no. If I flip that coin 1,000 more times, I would probably get something closer to 500 heads. Lots of people like to quote this law of averages that doesn't really exist. We are talking here about the law of large numbers. The more times you repeat the random phenomenon, the closer it gets to the true probability of each outcome happening. People like to quote this about like snowy winters. You know, we haven't had a snowy winter in a long time, so we're due for a snowy winter. Well, the weather doesn't know that we haven't had a snowy winter. And so the weather isn't just going to dump snow on us so we can have a week off of school because we haven't had that in a while. The same thing is true about flipping a coin. I think maybe I've asked a question here. So I flip a coin and I get 5 tails in a row. Do you think that you should bet your money on a heads coming up next because I've had a bunch of tails? Well, you might feel that way in your gut, but the coin doesn't know what you've been observing. So the coin doesn't know that, hey, I've been showing up tails. I should turn into heads now so I can get closer to a half. So the probability remains the same. It's still a 50% chance you flip that coin and get a tails or a heads. So we do have some rules about probability that you probably are already familiar with. Um, probability are values between 0 and 1. So an event, an outcome with 0% probability, like 0% chance it's going to rain, that means it will absolutely not happen. Probability of 1 is something is certainly going to happen. If we're in the middle, if we're a 0.5, so that probability of a heads and probability of tails, it's equally as likely that it's either one of those things. So the closer you get to 1, the stronger the chance something is going to happen. The closer you get to 0, the less likely that thing will happen. So if we have a set of possible outcomes, so before when we were flipping two coins, heads, heads, tails, heads, heads, tails, 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 the probabilities of each of those individual outcomes have to add up to 1. So the probability of for the entire sample space must add up to 1. And then we have this thing called the complement. Um, I guess it's similar to the complement in geometry where we have two angles that add to 90. So if you know how big one angle is, then you can find the other one because you know they're supposed to add up to 90. So if I know the probability of rolling a die and getting a 1 is 1 out of 6, then the probability of not getting a 1, all the other numbers, would be 1 minus 1 out of 6, so 5 over 6. And so that 5 over 6 is called the complement. So take a second and read this example. So I've been doing some data collection, and not really, this is from the book. And we hit a green light at this intersection about 35% of the time that we drive through it. And so that's an observed probability. So we want to know the probability the light is not green. That's the complement. That's being red or yellow. So we're looking for the probability of the complement of being green. We just do 1 minus the probability of being green, and we find that we have a 65% chance of driving through that intersection and either hitting a red light or a yellow light. And the yellow light means to slow down, everybody. It doesn't mean to speed up so you can make it through. We have a rule where we are, if we have two disjoint or mutually exclusive events, so that means that these things cannot happen at the same time. In the world of Venn diagrams, let me see if I can draw this with my mouse real quick. A Venn diagram is when we have the circles. This is terrible, but two mutually exclusive events would be where the circles don't overlap at all. They have nothing in common. They can't happen at the same time. So if we want to find out the probability of either of those events happening, we can just add those probabilities together. So if you don't remember, this little symbol means or. So this is the probability of event A or event B happening. And if they are mutually exclusive or disjoint, they cannot happen at the same time, then we just add those two probabilities together. Of course, if they are not mutually exclusive, that's going to be a different situation, and that's something we'll talk about in a future lesson. So here I'm adding to that example from the last page where I hit a green light 35% of the time. I also find that I hit a yellow light 4% of the time, so I want to know the probability of a red light. And so these are disjoint events. They're mutually exclusive. You can only hit a green or a red or a yellow. You can't hit more than one at a time. So if I want to know the probability of a green or a yellow, so those are the ones I'm not looking for, but I can find the probability of them together. I just add those two probabilities together and say that's 39%. And so not getting a green or yellow would be getting a red. And so if we find the complement of green and yellow, we will find the probability of red. So the probability of getting a red is the complement of the probability of getting green or yellow. So 1 minus that 0.39 is 0.61. So 61% of the time, we're hitting a red light. So buckle up, you're going to have to wait at the light. And the last rule is the multiplication rule. So we need to have two independent events to use this rule as it's written. Independent means that one event happening does not change the probability of the other event happening. So a way to illustrate independent events, we use playing cards a lot. If you're familiar with playing cards, a 52 card deck. If you draw a card, you have a 1 in 52 chance of drawing that card. And then if you put that card back in the deck, you still have a 1 in 52 chance of getting that same card. Okay, the probability doesn't change because it goes back into the deck and you could draw that card still. So those are independent events. If I drew that card and then I didn't put it back in the deck, the probability of drawing that card would change. That means that the first event changed the probability of the second event happening, and so those would not be independent events. So to use this multiplication rule as it's written, we need our events to be independent. They don't affect each other's probability. In the event that they're not independent, it's a different situation. We'll talk about that in a future lesson. So this simple means and. It's the one I believe would be really easy to turn into an A. Oop, you can't even see that. So the probability of event A and B, if those two events are independent, you just multiply the two probabilities together. So we're going to stick with our lights. We want to know the probability that I hit a red light on Monday and Tuesday. Well, hitting a red light on Monday is not going to change the probability of hitting a red light on Tuesday. The light doesn't know on Tuesday what it was on Monday. And so those two things are independent. And so since they're independent, I can just multiply the probability of getting a red on Monday and the probability of getting a red on Tuesday and find out that the probability of getting a red both days is 0.3721. So approximately a 37% chance you hit a red light Monday and Tuesday. So I want you to take a second, read through this, and I got a few questions associated with it that we'll talk about, and then we'll be done. So I think it's interesting, maybe some people don't know that, or maybe we talked about this in class, that there used to be a tan M&M, and that M&M, probably a little boring, was replaced with the blue M&M. And then they wanted to add another color, and so they surveyed, as they say, almost every country in the world. So they did a stratified sample, or as close to a stratified sample as they could get. They sampled a little bit in every country. So the countries were strata. There we go. We're making connections. And they eventually landed on purple. And so, but in this specific country, Japan, 38% of those who voted said pink, 36 said teal, and only 16% said purple. So we want to know, what is the probability that a Japanese M&M survey respondent, so somebody who answered that survey, if we randomly select from that group of people, what's the probability that they preferred either pink or teal? So an or probability means that we're going to add. Voting for pink or teal, those are mutually exclusive. You can only vote for one, so you can't vote for both at the same time. So we're allowed to use that addition rule. So we can just add the probability of voting for pink or teal. So that means our 38% who voted for pink, our 36% who voted for teal. And if we randomly select one person from that group, it's a 74% chance that they selected either one, pink or teal. Same idea. If we're picking from that pool of people, but this time we pick two people at random, we want to know the probability they both selected purple. So the probability the first and the second selected purple, that's an and probability. So we can use the multiplication rule if they're independent events, which they are. So if these two respondents are randomly selected, then one of their opinions is not going to affect the other person's opinion. So we can just multiply the probability that they liked purple best together and find out that out of that group, there's approximately a 2.6% chance we would have selected two people who chose purple, which should make sense because purple was the choice least chosen. The last one, if we pick three at random, the probability at least one preferred purple. So this is where we're going to use a complement. At least one means one, two, or three of them. And so the opposite of that would be that none of them chose purple. So let's find the probability that none of them chose purple. So that means the first one and the second one and the third one didn't choose purple. And then we're going to multiply those together because they're ands. And we're going to subtract them from 1 because that would be the complement. So it's an 84% chance that they didn't choose purple each time. Multiplied together and subtracted from 1 is approximately 41%. So we have approximately a 41% chance that we randomly select three people and at least one of them preferred purple. So this was definitely longer than normal. Thank you for making it the whole way. If you have questions, make sure you email me, message me, try some of those problems from the book or the PDF that I've posted. There's answers. Again, email me. Do as much as you need to so that you are prepared to crush the AP exam.